Double integrals. Let's start by doing a quick review of the Riemann integral from single variable calculus. The geometric motivation for the Riemann integral is to attempt to find the area under a curve that's above the x-axis and between two real numbers a and b, or between the two vertical lines x equals a and x equals b. The way we do this is we start by chopping up the interval from a to b into n subintervals. So we see here we have the interval from x0 to x1, from x1 to x2, and so on through xn minus 1 to xn. Notice that we named a x0 and b xn. We then take a real number in each of those subintervals. Those are labeled C1 through Cn in this picture. And we evaluate the function at that real number to get the height of a rectangle whose base is one of those subintervals. So for example, the first rectangle there has a base whose length goes from x0 to x1 and whose height is f of C1. And similarly for each of the other rectangles there. We'll generally call the length of each subinterval delta xi. So the length of the first subinterval from x0 to x1 is delta x1, and the length of the last subinterval from xn minus 1 to xn is delta xn. Notice that delta x1 is equal to x1 minus x0. Delta x2 would be x2 minus x1, and so on, up through delta xn is xn minus 1. So what we do now is we simply add up the areas of all those rectangles. So in other words, we have f of C1, that's the height of the first rectangle, times delta x1, which is the length of that rectangle, plus f of C2, delta x2, and so on. We can write that in this summation notation using the Greek letter sigma. So we see we have sigma, k goes from 1 to n, f of ck delta xk. That's the sum of the areas of all those rectangles. And then we take the limit of this process as n goes to infinity, and we call that the Riemann integral, or definite integral from a to b of f of x dx. And taking that limit gives us the exact area under that curve, as long as the function f of x satisfies certain reasonable conditions, meaning informally that the function is sufficiently nice. Let's now generalize this to 3 dimensions. So now we're going to start with a function of 2 variables, z equals f of xy. Its graph is a surface in 3-dimensional space. We're also going to take a region in the xy plane. We'll call that R. And we're interested in finding the volume of the solid that's generated from starting at the region and going straight upward until we hit the surface. So we want the volume under that surface and above the given region. We start by placing the region inside of a rectangle. As long as the region is bounded, we will be able to do this. We then chop up that rectangle into a bunch of subrectangles. For each subrectangle that contains part of the region, we take a point. Let's call that ck dk. And then we plug that point into the function. So we take f of ck dk to get the height of a rectangular solid whose base is that subrectangle. Finally, we add up the volumes of each of those rectangular solids. So f of ck dk is the height of one of those solids, and delta ak is the area of the subrectangle containing ck dk. We add all those up, so we have the sum as k goes from 1 to n of f of ck dk delta ak. And then if we take the limit as n goes to infinity of this process, we get the actual volume under the surface and above the region, assuming that the surface is above the xy plane and is sufficiently nice in the sense that the function f of xy doesn't have any major issues. For example, if it's a continuous function, we'll be okay, but actually even more general functions than that will work. We call this limit the double integral of f of xy over the region R. And you could see the notation that we use for that double integral there. We use the 2 integral symbols with a subscript of R, f of xy dA. Now, I just want to mention that in practice, we will never have to use this limit definition. Just like in single variable calculus, where we can compute definite integrals by doing anti-differentiation, we're going to do the same thing here. We're going to do what's called iterated integration. We're going to do two integrals to get the answer. We're going to start with partial integration, which is exactly the opposite of partial differentiation. So here are some examples to try. Without saying any more, I'm going to let you attempt these first. Pause the video, try these yourself. I think it's pretty self-explanatory what to do. You're just going to be doing the opposite of partial differentiation. Give it a try, and then resume the video to check your answers with mine. Okay, starting with the integral from 0 to 1 x cubed y dx. We're going to be pretending that y is constant here because we're doing a dx integral. Therefore, we just pretend that this is a regular definite integral from single variable calculus where y is being treated as constant. So notice I pulled the y outside of the integral symbol because we're not integrating with respect to y, we're integrating with respect to x. And now we could just do a power rule. So we have y times x to the fourth over 4 from 0 to 1. And using the fundamental theorem of calculus, we could plug in the 1 to get 1/4. We plug in the 0 to get 0 and subtract. So we just get 1/4. So we have y times 1/4, which is y over 4. Now we have the same integral dy instead of dx. So the integral from 0 to 1 x cubed y dy. This time, x is being treated as a constant, so we could pull the x cubed outside of the integral symbol. And now we're just doing x cubed integral from 0 to 1 y dy. By the power rule, we have x cubed y squared over 2 from 0 to 1. And again, we plug in the 1 and we get 1/2. We plug in the 0, we get 0. So it's just x cubed times 1/2 or x cubed over 2. Let's do one that's a little harder. The integral from 0 to 1 e to the xy dx. I'm going to do a substitution. Let u equal xy, then du is y dx. Remember, we're doing things with respect to x here. So we need to put in a y. I did that in green there, and I also multiplied by 1 over y outside the integral. We could pull that outside the integral because y is being treated as constant here. We can now make the substitution. In place of xy, we put u. In place of y dx, we put du. And notice that when x is equal to 0, u is 0 times y, which is also 0. That gives us the lower limit of the integral. And when x is equal to 1, u is equal to 1 times y, or y. That gives us the upper limit of the integral. This is now a straightforward integral. We have 1 over y e to the u. When we anti-differentiate e to the u, we just get e to the u. From 0 to y, we plug in the y, we get e to the y. We plug in the 0, we get e to the 0, which is 1. So we wind up with 1 over y times e to the y minus 1, or equivalently e to the y minus 1 over y. Now, as I've said, when we actually do a double integral, we're going to do what's called iterated integration. We're going to integrate with respect to y and then x, or with respect to x and then y. So here are some examples of iterated integrals. All you need to know to do these is to work from the inside out, to the inner integral first. That's just a partial integral like we just learned. And then do the outer integral, which is just going to be a definite integral from single variable calculus. Pause the video, give these a try, and then resume the video to check your answers with mine. So the first one, integral 0 to 2, integral 1 to 3, 4xy plus 1, dy dx. So we do the inner integral first. That's with respect to y. So x is being treated as a constant. So it's 4xy squared over 2, or 2xy squared plus y, from 1 to 3. When we plug in the 3, we get 2 times x times 9, or 18x plus 3. And then when we plug in the 1, we get 2x times 1 squared, or 2x plus 1. And we subtract those to get 16x plus 2. Now notice we just have a regular definite integral from single variable calculus, which we integrate in the usual way. We're just going to do a power rule here. 16x squared over 2 is 8x squared. And the 2 becomes 2x from 0 to 2. plug in the 2, we get 8 times 2 squared, or 8 times 4, or 32, plus 2 times 2, which is 4. And when we plug in the 0, we just get 0. So it's 32 plus 4, which is 36. For the second one, notice that the integrand here, 4xy plus 1, is the same. All we did was switch the order of integration. We have dx dy instead of dy dx, and we interchanged the limits on our integrals to be the reverse of what they were in the first example. So again, we're going to do the inner integral first. So this time we're integrating with respect to x, and we get 4x squared y over 2, or 2x squared y plus x from 0 to 2. When we plug in the 2, we get 2 times 4y, or 8y, plus 2. When we plug in the 0, we just get 0. Now we have a regular definite integral from single variable calculus. 8y squared over 2 is just 4y squared, plus 2y from 1 to 3. When we plug in the 3, we get 4 times 9, or 36, plus 2 times 3, or 6. And when we plug in the 1, we get 4 times 1 squared, or 4, plus 2 times 1, or 2. So this comes out to 36. Notice that in this case, the answers came out the same when we interchanged the order of integration here. This will always happen when we're doing a double integral over a rectangle. How do we know it's a rectangle? Because all the limits on the integral symbols are constant. So whenever the limits on the integral symbols are constant, you could interchange the order of integration and you will always get the same answer. Let's try one more example. Pause the video, try this example yourself, and then resume the video to check your answer. Evaluate the double integral over r x squared y dA over the rectangle r equals the set of points xy, such that x is between 0 and 1 inclusive, and y is between -3 and 2 inclusive. Okay, so we're being asked to compute this double integral. We're going to first change it to an iterated integral. I'm changing it to an iterated integral dx dy. So I'm going to be doing the x integral first, followed by the y. But by what I said at the end of the last example, you could have equally have done dy dx, just making sure to interchange the integrals as well in terms of what the limits are on them. Okay, but we'll do it this way. So we do the inner integral first, integrating with respect to x. X squared becomes x cubed over 3. So we have 1/3 x cubed y from 0 to 1. And when we plug in the 1, we just get 1/3 y. When we plug in the 0, we get 0. So this is now just the integral from -3 to 2, 1/3 y dy. Just a power rule. We get 1/3 y squared over 2, or 1/6 y squared from -3 to 2. When we plug in the 2, we get 2 squared, which is 4. When we plug in the -3, we get +9. So we have 1/6 times 4 minus 9, which is -5/6.